Our next speaker is Dr. Myron Allen. Now, I'm a historian of religion, and I don't talk about mathematics too often. But I recall my first conversation with Dr. Allen about math. I had been boldly trying to classify academic subjects into a limited number of groupings, and I had placed mathematics into the sciences. I thought this was sort of obvious. He took objection to this and argued that math should actually be considered a language. He posited that math was really a set of discourses whose rules enabled the accurate description of the physical world. In other words, a family of languages. I did not appreciate his view at the time, but consideration of his point since then has convinced me of its accuracy, at least for a specified value of accurate. Myron's interests have long leaned towards the description of the physical world. His 2 bachelor's degrees from Dartmouth were in mathematics and physics, while his 1983 PhD was in mathematical engineering. Upon its completion, he came straight to UW, where he has taught ever since, nearly 35 years of dedication to the institution and to the state. Now, Dr. Allen's research interests have focused on the movement of water through porous underground layers, big topic here in Wyoming, and related issues of fluid mechanics and thermodynamics. He's worked with teams of researchers to solve particular problems and then turned around to devise new insights into the math that helps solve them. The complexity of his research often involved detailed mathematical modeling, some of which requires massively parallel machines. In other words, supercomputers. Now, I must confess that Dr. Allen went over to the dark side for a little while, administration. But he did it with the same dedication that is apparent in his teaching. Indeed, his stint as provost coincided with UW's best years since the oil embargo of the 1970s. And now, for something completely different from all that, Dr. Allen will use his expertise to explain to us an idea bigger than we can imagine: how mathematicians grapple with infinity. Professor Allen.
I want to talk about this topic of infinity. We encounter this topic in lots of different informal ways, and I want to ask a question before I go any further. For how many of you was math your favorite subject in school? Be honest. You don't have to raise your hand. Okay, so for some of you it was your favorite subject in school. How many of you encountered the idea of infinity somewhere along the way in your math courses? Okay, so quite a few, even among people for whom it wasn't their favorite subject. Okay, so I want to take a look at infinity, maybe from a point of view that some of you may not have seen before. The first thing I want to do is delineate, to some extent, what I'm not going to talk about. There are a bunch of different notions of infinity, and so I want to clarify which one I'm going to be talking about for the next half hour or so. There's physical infinity, and that has to do with the question, is the cosmos finite? So that's an empirical question. Nobody has seen an end to the universe. We haven't figured out by other means, in less direct ways, whether the universe is finite or infinite. But I'm not going to be talking about that question. That's really a question for physicists and astronomers. There's the notion of spiritual infinity, and for many people that notion consists of the question, is there an infinitely powerful, infinitely knowing being? And there are many, many beliefs, probably quite a few different beliefs in this room about the answer to a question like that. The beliefs that people hold in this regard are justified in many, many different ways, almost never using mathematics. So this is not a mathematical question, and I won't be talking about that kind of infinity either. What I will be talking about is what I'll call logical infinity, what might we mean by the word infinity? What would be a good definition of it? And then from a logical point of view, what are the consequences of that definition? So that's the kind of infinity that I want to spend some time examining. This is a very old question. One of the oldest questions that scientists and philosophers and dreamers have considered. And Zeno, who lived almost 500 years before the Christian era, posed 9 different paradoxes that we know about. We don't know everything that he wrote, but he posed 9 paradoxes that we know about, including one that I want to focus on called the Dichotomy Paradox. And here's how that works. Let's suppose that we consider a person named Homer who has to travel a certain distance. Zeno posed the following argument. He said, well, we could divide Homer's progress up into stages. And in the first stage, he gets halfway to his destination. And in the second stage, he gets half of the remaining distance toward his destination. And in the third stage, he gets half of the remaining distance. So he travels halfway, then a quarter of the way, and then an eighth of the way, and so forth. And the argument that Zeno advanced was, well, since Homer must execute infinitely many of these stages to reach his destination, he can never get there. Now, Zeno was not a dumb guy. He did not believe that Homer could never get to his destination. But he posed the paradox as a way of asking the question, how are we going to grapple with motion when we can subdivide it into infinitely many stages? And we know that we can't do an infinite number of things in our lifetime. So that's Zeno's paradox, and I'll come back to it in a minute. Almost 2 millennia later, Galileo came along and posed what seemed to be a simpler paradox. And his paradox was the following. He said, well, you know, there are the counting numbers. 1, 2, 3, 4. I'll call them the natural numbers. So there are these natural numbers, the counting numbers, and then there are the squares of each of those numbers. So the square of 1 is 1, the square of 2 is 4, the square of 3 is 9, etc. And we could just draw this list of the squares of the numbers, and the list is just as long, apparently, as the list of natural numbers. So another way that we could think about Galileo's paradox is there's a one-to-one correspondence between the set of natural numbers, that's the counting numbers, 1, 2, 3, and 4, the first ones we ever knew, and the set of their squares. 1, 2, 1, 1, 4, 9, 16, etc. So in one sense, they seem to be sets of the same size. There's a one-to-one correspondence between them. But we know that the set of squares is just a proper subset of the set of all the whole numbers. So how can it be that those two sets seem to be the same size? The lists are equally long. For every natural number, there's exactly 1 square. For every perfect square, there's exactly 1 natural number. That seemed to Galileo to be paradoxical. That turns out to be a paradox that led to more surprising results, I would say, than Zeno's paradox. But Zeno's paradox was worthy in its own right, so I want to go examine Zeno's paradox a little more closely. It turns out both of the paradoxes are resolvable. It's possible to figure out what's going on with both paradoxes. But the resolutions are fundamentally different and yield fundamentally different insights into the nature of infinity. Let's take a look at the resolution of Zeno's dichotomy paradox. So just to make the arithmetic simple, let's just suppose that our friend Homer has to cover 1 mile, and he's going to do so at the leisurely pace of 1 mile an hour. So we all know how long it's going to take him to cover that mile, right? It's going to take him an hour to cover that mile. And we've done that ourselves. Covered a mile, maybe faster, maybe slower. But at any rate, let's just figure out the time that it takes for Homer to complete these different stages that Zeno was worried about. So if he, I haven't written it on the slide here, but if he just completes one stage, that's getting halfway through the mile, and he takes a half an hour to get there. If he completes 2 stages, he goes a half a mile, and then half the remaining distance, which is a quarter mile. And it takes him a half hour plus a quarter hour to get there. And so if we do just a little bit of thinking about that, we can see that it takes 1 hour minus a quarter hour. That's how much is left. So it takes him 1 minus a quarter hour to complete those 2 stages. The time it takes him to complete 3 stages is 1/2 hour plus 1/4 hour plus 1/8 hour, or we could think of it as 1 minus 1/8 hour, and so forth. You can see the pattern starting to emerge. The key point that I want to make about this little bit of arithmetic here is if we look down the list from 2 stages to 3 stages to 4 stages, etc., we can make this sum as close to 1 as we want, just by taking enough stages. Right? If we need to get within 1/32, we could go 5 stages, and so forth. That turns out to be the key to breaking the code for Zeno's paradox. We can get as close as we like to the final answer, which is 1. It takes him 1 hour to travel that mile. So let's look at this in a little bit more abstract way. So I wrote down those different sums, 1/2 plus a quarter, a half plus an eighth. In general, what we're doing when we take the next step, if we're taking, for example, the step number n, we are adding 1/2 plus 1/4 plus 1/8 all the way up to 1/2 to the power n. And what the time that it takes us is 1 hour minus 1/2 to the n. And as we take more and more steps and n gets bigger and bigger, that 1/2 to the n gets smaller and smaller and smaller, and we get as close as we like to 1. Well, so we could even ask the question, how many terms do we need to add? In other words, how many stages do we have to take to get within 1/1,000,000th of the final answer, 1 hour? And maybe you still feel pretty confident about working with exponents and logarithms, or maybe you don't. The point is not, I'm not giving a quiz here. The point is we can do this little calculation and figure out that to get within 1/1,000,000th of that final answer, 1, we'd have to take 20 terms. We'd have to travel for 20 stages, and that would be enough to get us within 1/1,000,000th of 1. 20 terms would be enough. And if we had an even stricter criterion, we wanted to get within 1/1,000,000th, we could figure out how many terms we'd have to take then. The point is, we can get as close as we like. Now we have a little bit of notation here that we use, and this notation can get pretty intimidating. What we will write is that if we could imagine adding up all of the terms, which we could never do, But if we could imagine doing it, we would write it using this summation notation. We're summing terms that look like 1 over 2 to the n, and we're summing them from n equals 1, n equals 2, all the way up to, and we'll just say we won't stop n equals 1 to infinity. And now comes something special. We will write that expression equals 1. Now, that just means, that's shorthand for meaning that we can get as close as we want to 1. It doesn't actually mean that we add up those terms, because we could never do that. But we can get as close as we want. This is essentially a new way to use the equal sign. Up until now, all the slides that I've had previously, we used it in a very standard way. Now we're using it in a new way to mean when we write that infinite sum equals 1, we say that means we can get as close as we like. That was the core idea in calculus. All right? The core idea in calculus is to deal with these infinite processes by saying we actually never do them. We just can get as close as we like. That's the idea of calculus. There was a ferment of activity starting in the 1600s with Isaac Newton and Wilhelm Leibniz. There was actually the first calculus book ever written was written by Maria Agnesi in Italy in the mid-1700s. And then we have to give credit to a fellow named Cauchy in the early 1800s who really solidified a lot of the theory here. And so some of you have probably encountered a calculus course. Maybe you loved it, maybe you hated it. But at any rate, it's a supremely useful discipline. Just to give an example of how useful it is, calculus underlies the design of every oscillating electric circuit, and there are hundreds of those in this room. If you have a watch, if you have a cell phone, if you have a smartphone, and there are all kinds of other devices that use an oscillating electronic circuit. So calculus has been really important for the advance of technology. And I'm sorry I hit too many buttons at once there. Okay, so the resolution of Zeno's paradox is we're just going to regard the equal sign in a new way, and we will think about these infinite processes in terms of getting as close as we wish. Fundamental idea behind calculus. Now, the resolution of Galileo's paradox, in some sense, starts off more simply, but ends up in a lot more tangled and fascinating story. So the first step in resolving Galileo's paradox, that's the paradox where the size of the set of natural numbers seems to be the same as the size of the set of their squares. So the first major headway in resolving this paradox was made by a German mathematician named Georg Cantor, who, well, you can see the dates of his life there, but he was really working in the 1870s and 1880s. Those were his heydays. And he began with Galileo's idea to try to figure out, first of all, how are we going to measure the size of sets? Well, here he just adopted a definition. He said 2 sets are the same size if there's a one-to-one correspondence between them. So you can see here I've got a yellow set called A and a green set called B, and for every point in A there's exactly 1 point in B, and for every point in B there's exactly 1 point in A. There's a one-to-one correspondence between those 2 sets. So we'll say the size of A is the same as the size of B. Now we do this from a very early age, right? We've all done this. We learn to count on our fingers. We're drawing a one-to-one correspondence between our fingers and whatever we're counting. So this is a very, very elementary idea in many sense. But if we adopt this definition, of two sets being the same size, then it turns out that Galileo was not blowing smoke. Those two sets, the set of natural numbers and the set of their squares, are the same size. Just a logical consequence of that definition. It seems very reasonable, especially if we think about how we counted things when we were 3 or 4. Okay, also, this definition of the same size gives us some idea about what we would mean if we talk about an infinite set. We'll say a set is an infinite set if it's at least the same size as the natural numbers. That's sort of our prototypical infinite set, right? A list that never ends. Well, so some people were disturbed by that definition and said, well, it's counterintuitive that the natural numbers would be the same size as the set of their squares. But Cantor proved something that was far more shocking. And so to talk about the next thing that he proved that was shocking, let's use this heavy Q to represent the set of all rational numbers. Maybe you remember what rational numbers are. If I take two whole numbers and take their ratio, that's a rational number. So it's the set of all quotients of whole numbers. Well, I got to be careful now. I can't divide by 0, so 0 can't be in the denominator. But otherwise, there's lots and lots of rational numbers. And I've drawn a little cartoon of a number line here. You know, it's got integers like -2, -1, 0, 1, and 2 sprinkled periodically along that number line. But in between all the integers are all kinds of rational numbers, right? I've got listed just a few of them: -9/5, -3/17, a half, 19/20. There's, between any two rational numbers, there's another rational number. But the easiest way to see that is just take their average. The average of those two numbers is between them. So the rational numbers are sprinkled not periodically but densely along the number line. It seems to be they're structurally different than the whole numbers, right? It would be counterintuitive, I think, to argue that the set of rational numbers has the same size as the set of whole numbers. But that's exactly what Cantor did. He came up with an argument that said, okay, I can list, of course, the natural numbers, 1, 2, 3, 4, 5, etc., and then alongside them, I can list the rational numbers in such a way that every rational number appears on the list somewhere. For every whole number, there's a rational number. For every rational number, there's a whole number. There's a one-to-one correspondence between them. So let's see how he did that. So first thing he said is, let's arrange this set in a big infinite table. And in the first row, we'll write all the numbers that have 0 in their numerator. Of course, they're all the same, right? They're all zeros. The second row will have all the rational numbers that have 1 in their numerators. The third row will have all the ones with -1 in their numerators, and so forth and so on. And although this is an infinite table, that you tell me which rational number you're interested in, I can tell you where it is in the table, right? Every rational number is in there. Now, if we go try to list the rational numbers, one possible way might be to say, well, let's just list all the ones in the first row, and then all the ones in the second row, and all the ones in the third row. The problem with that strategy is I'll never, for at least the second row, I'll never get to the end of it, and I'll never include any of the rational numbers that are in any of the other rows. And the same thing if I try to go down columns. I'll never get to the end of the first column to start picking up the rationals in the second column and so forth. So Cantor did the following. He said, let's just go through in a different way, and we'll sort of zigzag through this table in the following way. Of course, there'll be some repeats. So we go from 0 over 1 to 0 over -1. They're the same number. They're both 0. Then we get to 1. Okay, there's a new number. And then minus 1 over 1. I hope you can follow the red track with me. Minus 1 over 1. Then 1 over minus 1, that's not a new one. We'll have to skip over it. 0 over 2, we've seen 0 before. 0 over minus 2, we've got to skip that one. Then we get to 1 over 2, and so forth and so on. And once again, in this list, I can figure out, for any rational number, I can figure out where it is in the list. All right? And if I am careful about it, I can end up weaving through the array and coming up with an unexpected but perfectly valid one-to-one correspondence between the natural numbers, our counting numbers, and the rational numbers. And I've just listed the first few in the list here, but the point is the list never ends, but for every natural number there's a single rational number. For every rational number there's a single natural number. So that argument showed that the size of the set of rationals is the same as the size of the set of natural numbers. To many people, that was a counterintuitive result. They don't seem to look the same as sets when we think about them on the number line. But it was a fascinating result at the time. This might provoke a question. Do all infinite sets have the same size as the set of natural numbers? Right? A surprising one did. So maybe there's just one infinity, and they all are the same. Cantor's answer was no. There's more than one size of infinity. And in fact, the set of natural numbers is just the smallest of the infinities. The set of all real numbers, it turns out, is bigger. They seem to be sprinkled densely along the number line, just like the rational numbers, but it turns out there are far more real numbers than rational numbers. So the set of real numbers, well, you know, it has all the rational numbers in them. All the quotients are in there, but there's a whole lot of numbers that have no rational representation. They're not fractions. There's not a representation as a terminating or repeating decimal expansion or anything like that. They're numbers like the square root of 2 or pi, or you may remember a number called e, or 5 plus the cube root of 17. Those are all real numbers that are not rational. Cantor showed that that set of real numbers is bigger in a meaningful way than the set of natural numbers. I want to talk about his argument in some detail, so I want to make some preliminary observations. Cantor actually said, I want to make my problem a little easier. I'm going to show that the set of all real numbers that are just the ones between 0 and 1. He said there's more real numbers in that interval between 0 and 1 than there are whole numbers or integers or rationals. So that's what we'll focus on. We'll focus on that set that I denote by this heavy I of all the real numbers between 0 and 1. Each of those numbers has a decimal expansion. 0 point some digit followed by some digit followed by some digit, and so forth. So for example, 1 over 11, that's a real number. It's actually a rational number as well, but it's a real number between 0 and 1. And it has the decimal expansion 0.090909. It's a repeating decimal expansion. But I hope you get the idea. Every real number between 0 and 1 has this decimal expansion. For Cantor's purposes of showing that you can't produce a list, a one-to-one correspondence between the natural numbers and the real numbers in this interval between 0 and 1, it's enough just to produce a strategy that would defeat anybody's attempt to make such a list. So whatever strategy you have, or for whatever list you come up with, Cantor came up with a strategy that will defeat it by producing something that's guaranteed not to be in your list. And that's the argument I want to talk about. Cantor's, we call it Cantor's second diagonal trick. And so for any proposed one-to-one correspondence, I want to construct a number that's not in the list, a real number that's not in the list. And if we can do that, the list isn't a one-to-one correspondence after all, and we'll conclude that the size of the set of real numbers is greater than the size of natural numbers, and infinity comes in fundamentally different sizes, at least 2. We'll see that there's more to the story than that. Here's Cantor's second diagonal trick. So I walk up to Georg Cantor and I say, I've got this list, and this is the list of all the real numbers between 0 and 1, listed, and here's their decimal expansions. And I have to use some different symbols with subscripts here, but what you can see is that I've got the first one on the list, 0 point, and then there's a digit and another digit and another digit and another digit. And then the second number in the list has 0 point D, I'm calling it D21, D22, D23, etc. Just a bunch of digits, numbers from 0 through 9. Now I look at the ones that are along the diagonal. You know, the first digit in the first element of the list, the second decimal digit in the second element of the list, and so forth. And I pay attention to those. And then, I try to build a new real number. And I do it as follows. For the first digit of the new number, I'll call that C1, I'll just look at this D11, the first decimal digit of the first number in the list. And if that's not equal to a 3, I'm going to make the first digit of my new number a 3. Maybe you can see that that's going to guarantee that this new number can't be in the first position in the list. And then for the second decimal digit, C2, in the hundreds place, I'm going to look at D22, the second digit of the second number in the proposed list. And if that's not equal to 3, I'll set it equal to 3. If it's equal to a 3, I'll set it to something else. Let's just say 7. Guaranteed to be different from the second entry in the list. And I just keep on going this way. All right, at each stage, defining the appropriate decimal digit of the new number to be something that's different than the corresponding element in the list. By doing that, I build a number that differs from every real number that's in that list. And so my claim to Georg that I had all of the real numbers in a list just got defeated, because Cantor can build a number that's not in my list. Oops, here's one you missed. All right, and I don't care what list it is, this strategy will beat it. So the newly constructed number differs in the nth decimal digit, the decimal place, from the nth number in the proposed list. So it differs from every number in the list. Well, that was Cantor's second diagonal argument. Now we have at least 2 different sizes of infinity. A small one, like the size of the set of natural numbers, and a larger one, the size of the set of real numbers. Are there infinities of other sizes? It turns out that the answer to that question is yes, and Cantor found a way to build essentially a hierarchy of infinities. He said, you give me an infinite set, I'll give you a bigger one. Namely, the set of all subsets of the set you just gave me. It's guaranteed to be bigger. There's a proof of that. There's a logical proof that will show that. I won't try to do it here, but it's not a particularly hard proof. It just you have to sit in a quiet place and think about it. So for any infinite set, the set of its subsets is a larger infinite set. So this gives us a hierarchy, right? A set of all natural numbers, a set of all of its subsets, the set of all of the subsets of the subsets, and so forth, as many infinities I want. There's just a tower of infinities, each bigger than the ones below it. Well, that's a pretty shocking answer, I think, for a lot of people. There's lots and lots of different sizes of infinity. Even though some unusual sets happen to be the same size, there's still lots and lots of different, there's a hierarchy, an infinite hierarchy of infinities. Okay, well, so here's a third question. Are there any sizes of infinities other than those that we obtain in this way, by taking subsets of infinite sets, sets of subsets of infinite sets? Could I get any other sizes of infinity? Cantor thought the answer was no. But he could never prove it. He spent years trying to prove it. He could never prove that there are no other types of infinity. And people tried for years after that as well to prove it, and nobody could prove it. They couldn't prove that there were other sizes of infinity. They couldn't prove that there weren't. And so this went on for decades, I want to mention that within at least some of our lifespans, that question got answered in a very bizarre way. This is maybe the most striking discovery of all. A fellow named Paul Cohen, who died just a few years ago, discovered that within the axiom system that mathematicians use these days and have used for a century or more, there's no way to tell. There is no way to answer that question with the axiom systems of mathematics. One way to look at that is you could assume that there were different kinds of infinity, or you could assume what Cantor believed and that there aren't. And neither assumption would contradict all the other theorems of mathematics that we know. Neither assumption would upset that apple cart. Well, that's frustrating to mathematicians, right? We would like to think that somebody, if somebody were just clever enough, they could figure out how to prove it one way or the other. We can't.
Axiom system?
So an axiom system is a set of fundamental assumptions about sets, basically, and we deduce all of the subsequent theorems of mathematics from those axioms. Euclid. That was Euclid's idea back in the time of the ancient Greeks. Just adopt a small number of obvious-seeming assumptions and then build all of geometry, or in this case, all of mathematics, on that small set of axioms. We have a pretty commonly agreed upon set of axioms, and they're very productive, but there's no way to tell this question about infinities. Well, so I want to kind of wrap up what we found here by looking at this idea of infinity. We can resolve the ancient paradoxes. Zeno's paradoxes, there were several others, but they basically all get resolved in a similar way using calculus. Galileo's paradox, which we resolved in a different way. But some of the resolutions have very surprising consequences. And in particular, one of the surprising consequences is there's an infinite hierarchy of infinities. It's just a logical consequence of the definition of infinity. It's impossible to classify all the infinities completely using the axioms of mathematics. And that's maybe the most surprising result of all, that the axioms of mathematics are deficient in that respect. Just two additional remarks. You might say, well, why don't mathematicians just come along and add another axiom and settle the question once and for all? And I'll say this, mathematicians are extremely reluctant to fix the problem in that way. I mean, it seems like an artificial fix. So we would just have to figure out what axiom fit everybody's intuition. And our intuition about infinity is just too fallible and too diverse. Different people have different intuitions about this idea to justify this kind of tinkering and coming along and imposing some axiom that doesn't seem especially obvious or natural. So we just have to live with the state of affairs as it is. There's an infinite hierarchy of infinities, and we don't know how to classify them all. Yes?
I don't quite know how to phrase this. You've now established that there's an infinite number of infinities, right?
That's right.
Physics has been able to describe time almost as a blanket that exists in all using mathematics. Would this discovery of infinite number of infinities, can you extrapolate that? I mean, are we talking now like multiple dimensions? I mean, you have an infinite number of infinities and you have mathematics that describes concrete time and space. Are we looking kind of in the window of alternate realities then, because there's so much we can't even get our head around?
So I don't know if everybody got to hear the question. If I were to rephrase it in a short way, I would say the question is, well, you know, time we think of, physicists have thought of time as being sort of an infinite axis. And now we have different levels of infinity. Do we have, you know, sort of more physics beyond what we can perceive and maybe alternate realities? And I want to go back to my very first slide. Mathematicians and physicists have enjoyed a great relationship with each other for quite a few centuries, but physical questions are different than mathematical questions, and there's no telling what physicists are going to discover. They use mathematics a lot, but the question you ask is not actually a mathematical question. It's a question about what will physicists be able to discover using mathematics?
Yeah.
I don't know if there's any possibility they could use the differences of infinity in different types of logical infinity to infer any things about the infinite nature of the universe. We don't actually even know whether time is truly infinite, right? Nobody's lasted that long. So
No, it's not even the infinite time, it's just that time and space seem to be actually concrete.
Yeah.
And we, as mere mortals, understand, physicists seem to understand, but have a different understanding of time and space now.
right, they do. Thank you very much.